Good day. And the title of this seminar is Large AI Model Optimize the Wireless Network. This is Mingxiang from Royal Institute of Technology, Sweden. And so this is the outline of the seminar. First, I will introduce the background, and then also the core challenge, then the main idea, and then we illustrate the ideas through the two case study, then finally give the conclusion. Introduction. First, the large AI model or the large language model represent a new frontier in generative AI with powerful reasoning and inference capability built from the extensive pre-training. As we know, there is a many large AI model already. Common one include, for instance, ChatGPT, DeepSeek, Llama, BERT, BART, Grok, and so on. Large AI model has increased capability in reasoning and mathematics. Large AI model is also about two formulas that solve the optimization problem. And as we know, for the wireless communication, major problem, if not all, is optimization process. So the new trend is to explore the reasoning capability of the existing model. Since our existing model is already very powerful, instead of training more model. So if we use the large AI model as an optimizer for wireless network, it has the advantage of the better performance and the instruction, the optimization through a plain language, and also high adaptability and flexibility, and also interpretability, as we will show later on. Currently, the sixth generation mobile or 6G wireless network are in the intensive research stage. It's expected to deliver both high-speed communication and also processing sensing capability, creating significant demand on the spectrum and hardware resource. And among the many emerging technology of the 6G integrated sensing and communication, or namely ISAC, is being explored as a key technology. It will emerge of this sensing and communication into a unified and efficient system. So basically, the ISAC refers to a design paradigm in which radio sensing and communication system are integrated to efficiently utilize the context wireless hardware resource and even to pursue the mutual benefit as well as the corresponding enabling technology. The key benefit of ISAC including, for instance, enhanced performance, enhanced spectrum and energy efficiency, and reduced hardware cost and physical footprint. For instance, they can share the same hardware and enable new application. For instance, the autonomous driving, smart city, high precision indoor positioning, and so on. And key enabling technology of ISAC including, for instance, the multi-input, multi-output MIMO network. So the large number of the degree freedom created by the multi-antenna allow for the flexible beamforming design to generate directional beamforming towards both communication user and sensing target. And also UAV network, thanks to the controllable mobility of the UAV and the high-quality line or side network links, UAV are expected to enhance the ISAC performance and provide a wider coverage. And the race and reconfigurable intelligent surface race create a smart radio environment by intelligently steering signal to enhance both communication link and sensing beamform on demand. And also high frequency band, millimeter wave or terahertz system can utilize the massive bandwidth to enhance the both ultra-fast data rate and environment sensing with central meter processing. And then the core challenge is how to optimize the ISAC network, since it have the different objective in both some sensing and communication, and also the lot of the constraint. So the practical implementation of the ISAC system introduce forbidden optimization challenge. A typical optimization problem can normally formulate in this way. For instance, we try to minimize the some cost and also and also subject to a constraint. For the ISAC optimization is highly non-convex, so the objective function effects and the constraint are often non-convex and NP-hard, and make it difficult to find a global optimal. Also coupled variable, optimization variable X, for instance, the beamforming design, power allocation, UAV location are highly linked, affect the objective function simultaneously, and also the competition objective. And for the sensing and communication, there may have the inherent trade-off among them. And then the current optimization approach, including the both model-based and also data-driven method, they both have the benefit and also insufficient. For the model-based optimization, it required expertise knowledge, required domain knowledge in the single processing and optimization theory to formulate the problem, and it's also high complexity, and the computational intensive and for large-scale problem. And also it may have the suboptimal result. It's prone to converge to a suboptimal or local optimal point, especially for the non-convex scenario. And then they also have a scalability issue. They may suffer from the curse of dimensionality as network complexity increase. However, for the data-driven method, it also have the problem. For instance, the data hungry require massive high-quality data set for effective training, and also have poor adaptability. A model training for one scenario does not work for another one, limited flexibility, and also unstable convergence, exhibit the slow or unreliable convergence during the training, especially with reinforcement learning. And also depend on the expert knowledge, require the domain expert to decide, and for instance, for the neural network architecture and problem formulation. And meanwhile, the LLM or large language model represent a new frontier in the generative AI with powerful reasoning and inference capability built from intensive pre-training. Instead of rely on solely on traditional method, and we can use LLM as an intelligent component within larger established optimization frameworks to overcome their limitations. I mean, why couldn't we combine these two together? Then we try to create a new hybrid solution that both rigorous and adaptable, reduce the deployment bottleneck caused by the heavy reliance on the human expert or data. So the main idea is to fuse the LLM with the traditional optimization algorithm. The key idea is creating hybrid framework that leverages the both based on both sides. This approach moves beyond the trading LLM and the traditional algorithm as a competitor, and instead treat them as a collaborator. To combine the adaptability of LLM with the mathematical rigors of the traditional algorithm, we can reduce the need for intensive expert development for new problem. And for instance, the benefit of LLM is inference and reasoning capability and semantic understanding can be combined with the traditional solver with mathematical rigors and guaranteed processing. Then we can create a synergistic LLM solver. So the unified framework and in what each side provide. What LLM brings is wise and flexibility. And LLM have the knowledge integration and substantial inherent expert knowledge from pre-training or on its extensive data set, significantly reduce the expert dependency. It have adaptability, handling general optimization problem using more natural representation and adapting to the new scenario with minimum fine-tuning. And also the interpretability, their ability to process a natural language description and provide interpretability and flexibility advantage. For instance, we can just give the target or the constraint by natural language. And for the traditional algorithm, it have rigorous and processing and theoretical rigorous. For instance, most most like the convex optimization have the theoretical rigorous and the can provide converge guarantees. And the numerical processing there excel at the high dimensional complexity value computation by exporting grading information to precisely regulate the search direction and step size. For illustration, we will give two case concrete example. Is based on the ISAC for different scenario. First, the case is that based on our publication in early this year, published by IEEE Wireless Communication Letter, and our high-level goal is to utilize ARM to enhance the evolutionary algorithm for solving a complexity multi-objective optimization problem in a multi-UAV ISAC network. So the new is that we integrating ARM as a black box search operator into a framework of the evolutionary algorithm. And our system model is like that. We have a multi-UAV ISAC network consisting of K UAV and M1 user. So all UAV fly at a same altitude. So this constraint can be relaxed. And also the horizon coordinate is QK and denoted by XK and YK. And assume each user M is an extended target with its center massive located in this coordinate. For each time slot, the UAV, multi-UAV network transmit a set of unipower ISAC waveform, include the single for radar sensing and communication, super process together. And for the performance measurement, we use CRB band and to as the localization sensing. So the lower bound of the localization of the user M is CRB can be evaluated in this way. To evaluate the communication performance, we adopt the fair network utility optimization framework of the maximizing the sound log utility across all the user. It can be evaluated in this way. It's basically similar to the sound rate of all the user. For the performance of the location sensing, we use the log sum of the CRB of the all ground user as the second objective to be optimized. It's just a log of the sum of the CRB bound. So our goal is to find the trade-off between the communication and sensing in the multi-UAV network. So the optimization problem can be formulated in this way. We have two objective function. Objective first, we try to maximize the sound rate, as means the minimize the minus of the F1 is sound rate, and minimize the sensing CRB bound. So the constraint is like that. It's subject to the radar sensing power constraint and also communication power constraint and the UAV power constraint over a single UAV and the UAV location constraint. The UAV should be in a meaningful region. To solve the problem, we first introduce the decomposition method of the multi-objective optimization. For simplify, we rewrite our approach in this way. Our F1 delta is just the minus F1, F2 delta is F2, and then the constraint is this is the optimization variable for the different power of the radar and the communication, and also their coordination location. So to solve the problem, we use a decompensated sub-problem based on the Chebyshev method. It can be evaluated in this way. To solve the problem, we integrate the ARM as a search operator into the framework of the multi-objective evolutionary algorithm based on the decomposition. It included the process of the initialization, evolution, and update process. During evolution, ARM works as the black box crossover and mutation operator to generate the new point by pump engineering. For our ARM pump and we integrate the following three kind of information into the pump. For instance, we will give the airman the problem description. Airman is supposed to know the objective and the variable of the optimization and also the optimization task. And then also the in-context example, LM is supposed to know a few solution to the multi-objective programming and their corresponding fitness at the current subproblem. Then we'll give the clear instruction of LM to generate a new solution and with better result. So this is our pump of LM. So first tell them you're expert in the UAV ISAC with multi-objective. You're given the localization and how many objective and variable and objective, and then we give a few solution, and then ask the airman to produce a result. So this is the overall process of our proposed algorithm. We first, based on the evolutionary algorithm, we first give the input the population size, neighbor size, parent, new point, and then do the initialize. Then we generate the initial population and compute the object value. And then we use ARM to generate the new point. ARM reproduce the multiple offspring and update the solution and also the result until some maximum number of iteration achieved. And this is a numerical result, and in this figure we use a hypervalue. It's kind of the corresponding to the larger the better, corresponding to the sun rate. So here we can see this is our proposed algorithm have the best result. And in this figure, we shows the function value of f1 and f2, and also with of tilde, and the minimum, the beta. And then in here, we can see our proposed one have the minimum value, so it shows other better than the other benchmark value. Here is a concrete example of the two UAV. There is shows their location. And also here shows the power of communication and sensing. Especially for UAV1, as we can see, when the communication power decreases, the sensing power will be increased. And then for the UAV2, they keep the same. And then second example, we give the more advanced ARM. And then this is based on our more recent paper on the joint user association and the beamforming design for ISAC network with the ARM. And the paper is acceptable for RGB open journal of the communication. Our goal is to design a hybrid algorithm that can effectively solve a complexity mixed integral non-linear optimization problem in a multi-base station ISAC network. Then we integrate the AM with the convex-based optimization, mostly in the framework of the alternative optimization. So our system model is like this way. We use a ISAC network consists of K base station, each with M antenna, and the base station collectively serving n-ground communication user. And simultaneously, the base station perform radar sensing for Q target. The ISAC single transmitter for base station K in time slot L is given in this way. Is also include the communication single and the radar single. Our objective is try to maximize the sound rate of all the user, and then the subjective the constraint of the radar detection constraint. So the radar detection SNR should be larger than some minimum threshold. Then we'll have the parameter estimation constraint. We use the CRB bound should be minimum some threshold. Then the power budget constraint for each user, and also the user association constraint. That means each communication user should be associated to one of base station, and each base station should have more than one communication user associated with. So our overall flow is like that. Our core challenge is that the mixed integral nonlinear programming optimization problem. To solve it, we use two sub-problems. And first we solve the user association, then we solve the beamforming optimization by using the AO alternative optimization approach among these two sub-problems. First, LLM will solve the discrete user association problem and find one of the user association. With the optimized user association, the convex solver will find the optimal beamforming. And then with this beamforming, the LLM will find then another user association with a better result. In this way, the process will continuous iteration until it's converged. For the user association optimization, since we assume the fix the beamforming, the problem can be simplified in this way, and then we can obtain the initial user association strategy by solving the sub-problem one, P1. It can be evaluated in this way. To solve this user association problem, we use a Pong-Pong-based ARM as a black box optimizer. So the ARM is guided through the structural reasoning, processing user multi-part pumping. So each part serves a specified purpose to transfer the ARM into a spatial blank box optimizer. First, for the ARM, first we give the background description. We tell the rule assignment. The pump always become you are expert in wireless communication to guide the AM. Then we have in-context learning. AM is inform the system model and expert knowledge. For instance, the Shannon capacity, and to evaluate the sound rate. Then we give the AM the concrete problem and the task instruction. For the problem description, the objective and the constraint are clearly stated in the natural language. Then we use the chain of the sort reasoning. The aim is guided to formulate the problem and solve it step by step. Here we use the chain with sort, then the problem will be solved in step by step method. Then we are able to have the self-reflection and to guide the search direction, ARM is pumped with its previous output, the older user association and the performance of older sound rate. So we guide the ARM that we have the generate a new solution with a higher sound rate. Then we create an iterative loop with improvement performance. And then finally, we'll formulate the output of the AM, and we will straightly formulate the pump space the exact output format, for instance, the matrix, and forbid the extra text. Otherwise, the output of AM will be very wordy, and that's to ensure the output is machine readable. So this is how our AM looks like. We give the background description, then the optimization problem description, and then task description. The ARM can generate the optimization problem. Then here we have iterative loop, and have the chain of the sort and the self reflection. Then finally format the output. So given the user association strategy from the ARM, the base station will optimize the beamforming by the convex based optimization method. And however, the problem is still non-convex. To transfer the problem into the convex one, we use the tool of the functional programming, majority minimization, and ADM, and then we can transfer the problem into the convex one and solve its exist tool. Here is some numeric result, and here is the average rate. Of course, is higher the better. Here we use the convex optimization plus the ARM GPT-01, and then we compare the convex plus the brute force When the number of the base station and the user is small, then we can use the brute force approach. Also, we can say our GPT-01 and the brute force worms have the same result. And for the other ARM and the convex not have the degraded performance. If we don't do the user association and only have the beamforming design optimization, then performance is the worst. And here is the X is the number of user and also Y is still the sound rate. As we can see, our GPT-01 also have the similar performance as the convex plus the brute force. That's the best optimal performance, and also have better. There are better than the other large language model. Here is also some other numerical result with different X. For instance, the number of antenna and the transmission power and the CRB threshold. We all have the similar result. And the GPT-01 in our experiment have the best performance. And the conclusion is that we explore the powerful inference capability of ARM to optimize the wireless network. ARM shows the excellent optimization in the evolutionary algorithm. ARM also shows excellent performance, close to optimal in the convex optimization. The choice of ARM model is very important. As we can see in the numerical result, GPT-01 seems to have the best performance. And then in pump design and channel sort self-reflecting and output formatting can effectively improve the performance. ARM shows the clear benefit of interoperability, flexibility, and least training cost, and also improvement of performance.